Hi, this is Discrete Math 5.1, Planarity and Coloring. So either in last class or in the beginning of next class, you'll go through this, but can you connect three houses to three wells? Now here's a stipulation. Here I did three houses to three wells. In a very arid country, they have a problem because they want to connect to different wells because sometimes this well is full and other times this one's full, so on. However, the three families don't get along that live in these houses, so you do not want to cross paths at all. So in other words, I want to try to take, see how this one crosses right here? I can't do that, so I might have to bring it around. Try this with these three and see what happens. I'm going to give you the answer, so pause this, and then we can also try it, like I said, in class. Now you should have found out through practice that this is impossible. And we'll look at it a little bit more in class, as I said. Okay, now this gives us an example. This is what we would call a bipartite graph. We'll talk about that in a little bit. But the objectives for this lesson would be to identify planar and non-planar graphs, identify subgraphs and bipartite graphs. Key part of that is bi, and then identify and write complete graph notation and bipartite notation. That's very easy. We've already done complete graph notation previously, yeah. Definitions: planar graph, a graph that can be drawn with no edges intersecting except at a vertex. And so the edges can't cross over each other. Bipartite graph, a graph whose vertices can be divided into two distinct sets so that each edge of the graph has a vertex in each set. Blah, blah, blah. Essentially, you have two sets of vertices and you can't connect within each one of those sets, but you connect to the opposite side. We'll show you. Subgraph is a graph that has all of its edges in another graph, and so it's just a small piece of a bigger graph. So now let's look at some of these things. K4 and K5, are these planar? If they are planar, you can elasticize them so no edges cross. So if I look at this, right now I have the vertices. I put them out as distinct dots. And so right now I have a crossing. So if you pretend that these are rubber bands, can I move one of these so that they do not cross? So here I put this on a geoboard. And so here's a K4. K4, remember, is a complete graph. So if I have four vertices, I connect each vertex with all the other ones. So if I look at this, what I can do is I can grab this and I can take this and put it outside. That is perfectly legal. So if you think about these edges as being elastic bands or rubber bands, and then you can move them around, that is helpful. You can also move vertices, believe it or not. And so if I wanted to move this vertex around, I could. Well, that didn't work out as good as I planned because I have this one too, but I can do that. This is exactly the same graph. It just has a little bit different shape to it. Okay, so that's what we're going to be doing. So are these planar? I just showed that this one is planar because I can show that they don't cross. This is a K5 graph. So I have 5 vertices, complete graph because each vertex is connected to each other one. And I put the word no here. Uh-oh. Let's try this one and see what happens. So my objective again is to grab one of these edges and then I can maybe pull it outside. And so now I just eliminated some of the crosses. Now I don't really create a new vertex here. Think of this as just a loop around, but that's what we're doing. Now if I take this one and do the same, I can pull that one outside. Now if I take one of these and, uh-oh, what happens now? If I take this one outside, I'm going to get a cross. Now I can't go exactly over the top. That's not legal. And so what happens is that I cannot get this edge out. Similarly, I can't get this edge in here out. This one, it's not crossing anything anyway, so I don't want to deal with it. So what happens with this K5 graph is that it is not planar because I can't resolve these two in the middle. So on your note sheet here, you can try this yourself and see if you can monkey around with that. But the answer for this is no. This is not a planar graph. K4, yes. K5, no. Now what happens is that if you have future graphs that have a K5 within them, then straight away you can say not planar, because K5 is not planar, and so I can't resolve the K5. Why can I resolve added items to it? I can't, right? So then this kind of answers, maybe it answers, maybe it's not clear, I don't know. But what are the most colors that we need to color a planar graph? Well, at most, we would need 4 colors, because once we get to this situation, we're in trouble. Now, what that does is that represents a relationship between a map and a planar graph. So if I take this, 4 would be the most colors. And this is how we represent maps. A map is an example of a planar graph. So this will follow the 4-color problem. If a graph is planar, it will need at most four colors to color the graph. Now what about vice versa? What if I said I only needed 2 colors to color a graph? Does that mean that that is planar? Well, we'll find out in a little bit. Unfortunately, we'll give you the answer right now. But however, the converse is false. You can have a 2-color graph that is not planar. So we have to look out for that. Now I have one last question down here. I say, should we even try a K6? No, we don't even have to try. Why? Well, to do a K6, all we're doing is taking a K5 and adding one more vertex. It's like the handshake problem. 5 people have already shook each other's hands. One new person comes into the room and shakes everybody else's. Well, if I can't have a planar graph for a K5, I can't do it for a K6. And so we would need 6 colors to color this. Plus, K5 is a subgraph, right? So then we run into trouble. So if you need 6 colors to color it, it can't be planar. Moving on. How are we doing? Hopefully all right. Bipartite. The bi means 2. Yep. So what we want to do is see if we can split the vertices into 2 distinct groups. And if we can do that and connect them to the opposite group but not within the group, then we have a bipartite graph. Both of these below are a bipartite graph. Now for a complete graph, where I have this vertex connects to 2 on the opposite side, so it has 2 edges from it. This vertex connects to the 3 on the opposite side, so it has 3 with it. Since all of these are full, all the connections are full, this is a complete bipartite graph. And so what we call that is a K32 and a K24 for each one of these respectively. So this one is connected to all 1, 2, 3, 4, 5 over here. This one's connected to all 5 and vice versa. It would not be complete, for instance, if this edge right here is not there, it is not complete anymore. All right, what's the chromatic number? Well, I could use red here, and then I could use blue over here. It's always going to be 2. 2 would be how many colors you need for a bipartite graph. Why? Because we can put them into 2 distinct groups, and you're connecting from one group to the opposite group, but not within its own group. And then how do we label these? I already labeled them down here, but it would be K sub Mn, where M and N are the number of vertices in each respective group. So I did that here, 3, 2, 2, 4. I don't know if the order matters or not, but we'll do it that way. All right, examples. Are these planar? I'm going to have to go to the drawings here to try to figure this out. This looks like a K5, but it's missing one edge. Does that one edge make a difference to try to deal with this? Well, let's find out. So if I start treating this one like it is elastic bands, I could do that. So I could take this edge right here and bring it over here. And I can just try this, how about this one? Bring it over here. And so now what I have, I still have these 2 crossing. So if I bring this, I can't do that. If I bring, I can't do that. That doesn't work. And so I run into trouble with this one in trying to find out if it is going to be planar or not. So there is another tactic you can do, and that tactic is possibly redrawing the whole thing. So that's what I'm going to do. Now, if I look at this one, I have B and C are not connected. So what I'm going to do is I'm going to create something around B, and maybe I can hang out with C and keep it outside and maybe make it work. So what I mean by that is, how about if I do B? Now, if you notice, B is connected to A, C, and D. So I'm going to put those around. So I got A, C, and D. So B is connected to all those. It has 3 segments from it, still has 3 segments. So I'm just doing the same exact graph, but a different representation. Now, if I look at A is connected to C and D as well. And C and D are connected to each other. Now we have the other item, which is the C. So I'm going to put the C out here. Well, what's C connected to? Well, C is connected to A, E, and D. Oh, I called this wrong. Sorry, this is E. And so what I do then, I made a mistake on that. I hope you got that. So then I got this here. This is C. C is connected to E. C is connected to A. And C is connected to D. Wow, that's the same exact graph. It looks different, doesn't it? However, it is the same exact graph with the same connections. It's just now I rewrote it, and so this is a planar graph. So the answer for this one is yes, it is planar. And we drew it without any crosses. If we had a chromatic number on this one, what's my chromatic number? I don't know if you can tell these colors. I try to put the letter on them for that, but this is one I made brown, this one I made brown. Why could I do B and C as the same color? Well, they're not connected. But then the other ones are connected to everything else, so I had to make those different colors, but I would end up with a chromatic number of 4. 4 is the minimum amount of colors I need to color this graph. That's the chromatic number. Now looking at this one, is this one planar? Yes or no? Well, I hope you can look at this one quite fast and say no. Why would that one be no? Well, I think it's pretty obvious here. You see a K5. Remember that we said if we had a K5 subgroup, a subgraph, and then we could not have that be planar. Anything that has a K5, I can't make this planar. So adding things in, I can't make that planar either. And so this is a K5 subgraph. If it has a K5 subgraph, it is not planar. All right? Now let's look at these last two that are bipartite, possibly. Now on your sheet, these vertices probably don't show up in color. Since they do show up in color, that makes life a lot easier for us. And so what we can do is we can label these. I'm going to use the pen. This one is A, and then I can go B, C, D, and I can call this one E. So those are my different colors. And now if I do the blue vertices, so now a couple of things here. I labeled all these vertices because I want to draw this out, but if you notice, this A is connected to a G, but it is never connected to these other red ones. And so A, B, C, D, and E can all be in one group. F, G, H, I, J, K can also be in another group. And so this is bipartite. So this one is yes, bipartite. Now, is it planar? Well, what I did was I went and took these values, A, B, C, D, and I connected them up. So if I look at this, this is A. A is connected to F, G, H, and I. So I connected all those. But it is not connected to J and K. But if you look at this, I did this for all of these vertices. This is a mess. There's no way you can take your rubber bands and play it out. Now, we did not make big mention of this, but if it has a K33 subgraph, then it is not planar. Well, this one actually, I don't think it has a K33 subgraph. I'm not sure exactly. However, it's just such a mess that there's no way that this would ever be planar. So this one is not planar. So it's a no there. Okay. Now this last one, is this one bipartite? Well, if you look at this, we have a problem at B, and probably the colors didn't show up on your notes, but we have a problem at B because B is connected within its group, and it's also connected opposite. Or you could say that B could be over in this group, but is also connected over here with C. Regardless, B is connected to both groups, and so this is not bipartite. Now the next question is it planar? Well, I'm going to let you figure that out and try to look at that one and see if you can play around with that and get the edges to make it planar or not. It might be, we don't know. So to finish this up, here's some additional notes you might want to get in there. But to finish this up, I've got, if a graph has a K5 or a K33 subgraph, it is not planar. It's not going to be planar. So if you can identify those things, then you know straight away it's not planar. For example, this one right here is a K55. I don't have a K33 on these examples, but this is a K32. This one should be planar. But anything beyond that K33 is not planar. I'm going to guess that this one's not. I haven't looked at it too closely, but I'm going to guess that it's not either. Okay, so I had this in here. You might want to put this back in your notes too. I missed over this. But any complete graph with n greater than 4, we need n colors to color this. Okay? All right. That's all we have. This turned into a little bit long, a long video. I'm sorry about that, but I hope you have a great day. Thanks.